Hello, everybody. We are Next Level Innovation, and we are going to be presenting to you our assembly arm, also known as the Grappler 1000. My name is Salma. I am the General Manager, VP of Operations, Marketing, and Sales.
Hi, my name is John Anderson. I'm the VP of Engineering and New Product Development.
I'm Kate De Silva, and I'm the Chief Financial Officer and Director of Procurement.
I'm Jonathan Salguero, Product Support Manager and Director of Compliance.
My name is Daniel Velasco, and I'm the Director of Product Design and Quality Control.
So here's just a quick rundown of what we'll be talking to you guys about today. We'll go over our project scope and goals, and then we'll introduce to you the Grappler 1000. We'll also talk to you about our manufacturing, competition, and marketing. So our mission as a group is to use engineering principles to create innovative solutions to manufacturing problems. And to do that, our project scope is to create an arm that would be user-friendly, ergonomic, lightweight, and modular to assist in the assembly process of manufacturing.
So what's wrong with the current withholding? The devices in current market cannot use for any kind of parts because of the way it designed. It has the limitation of the uses. Also, most of them are operated by manually and non-ergonomic and taking too long to set up and adjust.
Taking into account the current limitations of work holdings, we wanted to create some goals for our product. So the first would be to use ball joints that would allow us to have multiple degrees of free motion. Those ball joints would be activated with a pneumatic system that can be controlled with a foot pedal. We would want our whole arm to be manufactured with lightweight material to allow for ergonomic design and ease of use. And finally, we want to demonstrate that it is modular by presenting to you two different end effectors.
This is our product, the Grappler 1000. You can see the limbs attached to it, and our goal was to achieve that rotational capacity with the degrees of freedoms, be able to move the limbs around, have the operator be able to put whatever workpiece they're working on in any orientation that they need it to, and be able to grip any workpiece that they need to by being able to switch out different end effectors. Next slide. So the manufacturing industry is evolving, and parts don't have simple geometries anymore that bench vices can grip onto. With the rise of generative design and additive manufacturing, part shapes are becoming a lot more organic and harder to hold on to. And because of this, traditional work holding isn't as dependable. This is where the Grappler 1000 comes in, and our assembly arm can hold all of these parts and be easily modified to hold any others. It's the future of work holding. Next slide.
So the Grappler 1000 is comprised of 5 main features. That's going to be the base, the limbs, pneumatic system, joints, and end effectors. This picture shows the Grappler 1000 in an expanded view, so you can easily see all 5 components very easily. And if you go to the next slide, you can get into the base. The base is made out of steel. We use the CNC milled and welding processes to manufacture it. The key features are these slots shown in the picture that's going to allow for the base to be bolted down to a workstation, such as a table or a bench. The 2 small holes in the top right are the indicator lights that are going to turn on with each activation of the joints, as well as on the bottom picture, we have an undercarriage channel for pneumatic and electronic systems to freely travel through the system so that they don't get snagged or anything. It'll be very ergonomic. Next.
So next up from the base, we have the limbs. The major function of these are to provide structure for the arm, as well as reach for a technician when they are operating it. They also house some of internal components that enable the unlocking feature of the ball joints. And these are 1.5 inch in diameter, and that size was a balance between hand feel, compacting stuff, and the stiffness. They are made of carbon fiber reinforced plastic, and we chose carbon fiber because of its lightweight and high stiffness. This means there is minimal deflection in the members when a load is applied to them. thus making the arm very rigid. They are made with 8 layers of 2 different carbon fabrics, and the picture on the left is a 0 to 90 degree weave that provides strength in 2 directions, while the unidirectional fiber on the right provides high stiffness in the arm under load. And the process we used to manufacture these was hand layup coupled with roll wrapping and curing it in an oven. Next slide. So up next is the pneumatic system, which uses air pressure to do work. The function of this is to actuate the unlocking mechanism of the arm. This is done using a linear motion actuator that you see on the left, and it retracts a spring within each joint. The system will work with any common 100 PSI source commonly found in workshops, and we couple the system with an internal air pressure regulator to ensure that the arm has the correct pressure at all times. We also added a moisture filter to prevent corrosion in the system since compressed air forms condensation. And a safety feature we added was a pressure relief valve that vents excess pressure to the atmosphere if the system is overpressurized. And to operate it, we use 2 robust foot pedals. Each pedal controls 1 joint, and it is ergonomic, and they work by allowing compressed air to flow into the pneumatic actuators when depressed. And they are simple, inexpensive, and low maintenance. Next slide.
These are the locking joints that keep the workpiece stationary when it's being worked on. They're in a normally closed position until the actuator is triggered and the internal spring is compressed to unlock the joint. The majority of components were made in our machine shop using a manual lathe and a CNC mill. The divots on the ball and the machining bumps on the housing tops are key to keep the joints locked when the piece is being worked on. Next slide.
At the end of the arm, we have a 1-inch by C collet mechanism, which gives the arm its versatility. This enables different end effectors to attach it and provide unlimited amount of work holding setups. Our arm currently supports small to medium-sized parts weighing about 15 pounds. And for demonstration, we created 2 different end effectors. On the left picture, we have an inner diameter bore holder, which allows operators to hold cylindrical feature parts that have about a 1-inch diameter. And the end effector on the right is the fixture plate with several slots and holes in it that allow an operator to bolt an array of different parts while they perform work. And that one was made out of carbon because it's lightweight and we didn't want to create a moment on the arm. And we used a CNC router to create that. Next slide.
This is what our production flow would look like if we took the arm to production. The chart gives a high-level overview of the manufacturing operations that are required to make the major components of the arms. This would be generated by a pull production system, and these only include the parts that we would make in-house and set up the workspace for. They'd happen concurrently, and typical machinery that would use our CNC mills and lathes with some possible manual machines, and then also composite tooling, drilling, and welding. After everything is assembled, it's inspected and tested for quality and then shipped to the customer. Next slide.
And this is the calculation of our unit cost. We used our bill of material to calculate our material cost. We made calculate for the cost for the 1 unit and the mass production. So for the mass production, we use 1,000 units. For the unit cost for 1 unit, we got $1,254, and for the mass production, it can lower it to $1,030. And for the calculate to selling price, we used a rate of return of 20%, and we came up with for the 1 unit selling price for $1,350, and for the mass production selling price for $1,300. Next slide, please. We are going to continuously improve our product. Currently, our Grappler 1000 can hold up to 15 pounds, but we can increase the weight capacity. Also, we can use different end effectors. So on the picture, we can use as a claw. Also, magnetic end effectors. So magnetic end effectors can really useful for the customers who work with metals. And currently, the ball joints are lock-in separately, but we can add another option to activate multiple joints at once. Also, we are going to add end effector lights, which will increase the end user's visibility. And rather than using the metal base, right, currently we are using, we can use vacuum base and electromagnetic bases. Next slide. Our target markets are the companies with high mix of parts and also mid to large manufacturing companies. Medical, they can use our product for the medical lighting on the surgeries, and paint companies, electrical companies, and composite companies also for the quality control departments. And there's some of the companies that fit into our categories are OnTech and Moog.
While we don't have anyone that has exactly what we do have some competition in the market. The first offering is going to be the Charleston Robotics Viper X300 robotic arm. The main problem with them is that their weight capacity is limited to 750 grams. We offer up to 15 pounds, and they're also at the range of 4,500. The middle, we have the traditional bench vise. It is easy to find, however, it's very non-customizable and non-modular like ours is. And on the far right is the Pneumatic. It is cheap. It's only $85, but similar to the other ones, it's not customizable and it's not very practical for use. Next slide.
As Jonathan mentioned, we need to attract the market towards our product, and the best way for us to do that would be for us to demonstrate this at trade shows and conventions like AeroDef and WestTech. We are also in a very prime location of manufacturing facilities, so we can contact companies like Moog and offer to demonstrate to them, or come there and demonstrate to them how our product would work well in their facility. Along with that, we could also use social media, especially platforms like YouTube and Instagram, where we can use paid advertising that would appear to people that are interested in this product. Finally, we can direct everybody to our website where they can place orders, and also they can read more about the new innovations we will offer.
Here we have a demonstration video of our assembly arm. When you depress the beige pedal, you're able to unlock the first joint and move it to a position that you want. You can press the blue pedal and move the arm to another position that would be better. Depressing the beige pedal again, you can move the first arm. And then depressing the blue pedal once more, you can move the arm into another position.
And just before we end, we wanted to give a special thank you to our advisor, Professor Elias, as well as our department head, Dr. Bavarian, all those who helped us in the machine shop, so Kaveh, Neil, and Caesar, and also our partnering senior design team, Go Gloves. Also, we want to give a special thank you to our sponsor, Performance Composites, who helped us out with materials and machining capabilities. Thank you.
Okay, thank you very much. Thank you very much. We are now open the floor to questions and answers. We have until 1:52.
Hi, this is Cash, and I have a question. What's the payload of this? I mean, how much weight you can put on the top of this?
The arm's designed to hold about 15 pounds.
Okay, and how the joints are holding the pressure? I mean, you can adjust the pressure, or how do you actually hold on those joints? You know, is that by adjusting the pressure if you want to go higher weight or lower weight?
No, currently it doesn't. So with this arm, it's only designed to hold up to 15. Okay. The joints are held in place by a compressed spring on the inside of the locking joints. And then that spring is further compressed by the actuators to allow the ball joints to drop with the retainer. Okay. And the ball joints also have like a matching divot bump set to increase the friction that the balls would feel to prevent it from rotating and slipping.
Thank you, ma'am.
Hey, team, let me congratulate you all for working together like this. It's a joy to see senior design go through something without a pandemic, but you all were able to pull this off in a pandemic, and it look as professional as what we do and produce for NASA in the country. So I commend you on that. You guys are on your way. Yeah, I gotta water the flowers, you know. Question I have for you quickly is what was it like, working as a team during this pandemic?
It was definitely a challenge considering our resources, but it was a joy to work with everybody, especially our team members have great industry experience, and we were able to learn a lot from each other.
Great. Love to hear it.
I just have a comment. It's taken me 40 years to learn some of the stuff you guys are presenting here today. So such a good job on bills of materials and how things get made. And this is really kudos to you. It's great stuff.
Thank you.
Your advisor and I went through this 150 years ago, Gus and I. Yeah. And Dr. V was our advisor.
I have a couple of questions, guys. So you landed on 3 DOFs, 3 degrees of freedom, is that right, for the arm?
Well, so each ball can rotate, so you can get the full, I think, 6 degrees of freedom in addition to the swing motion. And then the smaller joint also has 4 cuts in it, as opposed to the larger one, which only has 3.
Yeah, so I wanted to ask about, did you think much about the control scheme and the control system that might need to go along with this, and how you might control the arm, control joint position, if there was any confirmation of being in a position or being open, closed, those kinds of things?
Right. So it's not a robotic arm. It's designed to be moved manually by the operator.
Oh, and the operator actuates the spring.
Yeah. So from my industry experience, I didn't want the operator to have to hold a part in position while like trying to lock it in place. Right.
No, that makes a lot of sense. Thanks for clarifying that. And then I just wanted to ask a little more detail about how you landed on carbon fiber for the links versus an aluminum, and thinking in particular about mass production and what one production style might look like versus another.
Well,
Danny, you want to answer that one?
We use carbon fiber for the limbs. Wasn't necessarily for it was the links, I guess, the limbs. We do know it's you can buy it in stock form now, so that it's not a huge limitation. But we made ours for the project. But as opposed to aluminum, the only reason why we didn't go with it is because of fatigue properties. Because possibly after its life, through its lifespan, maybe the aluminum would fatigue before the carbon, and also the corrosion part of it. Yeah, I don't know if that clarifies your question.
So, folks, it's 1:54. The next round starts for the mechanical engineering folks at 1:55. So we need to cut the questions and answers, bring that to an end.
Thanks,
Great job, MSEM. Go Matadors.
Yeah.
Thank you, Coach.
You guys are the Avengers.
Thank you, everyone.
Thank you.